Welcome everybody to module 4 Predictive Analytics. In this learning session, we'll learn about genetic algorithms and bi-inspired modeling. We will then use bi-inspired computation, its algorithm called ant colony optimization, popularly known as ACO, to solve a very famous troubling salesman problem. Basic focus of this session is about understanding what are genetic algorithm, bi-inspired modeling. This helps in implementation of ant colony algorithm for troubling salesman problem, which has immense implication in industries. After scientists became disillusioned with the classical and neoclassical attempts at modeling intelligence, they looked in some other directions. Two prominent fields that came to limelight are connectionism, that is neural networking, parallel processing, and evolutionary computing. It is the latter one that this learning session deals with special focus on genetic algorithms and genetic programming. A genetic algorithm, popularly known as GA, is a search technique used in computing to find true or approximate solutions to optimize and search problems. Genetic algorithms are categorized as global search heuristics. They are particularly class of evolutionary algorithms that use techniques inspired by evolutionary biology such as inheritance, mutation, selection and crossover, also called as recombination. Genetic algorithms are implemented as a computer simulation in which a population of abstract representations called chromosomes or the genotype or the genome of candidate solution called individuals, creations or phenotypes to an optimization problem evolves towards better solutions. Traditionally, solutions are represented in binary as string of zeros and ones, but other encodings are also possible. The evolution usually starts from a population of randomly generated individuals and happens in generations. In each generation, the fitness of every individual in the population is evaluated. Multiple individuals are selected from the current population based on their fitness and modified, recombined and possibly mutated to form a new population. The new population is then used in the next iteration of the algorithm. Commonly, the algorithm terminates when either a maximum number of generation has been produced or a satisfactory fitness level has been reached for the population. If algorithm has terminated due to a maximum number of generations, a satisfactory solution may or may not have been reached. So, we come to the bi-inspired computation using the intelligence that the animals usually use. So, bi-inspired modeling is a field of study that loosely knits together subfields related to the topics of connectionism, social behavior and emergence. It is often closely related to the field of artificial intelligence, as many of its pursuits can be linked to machine learning. It relies heavily on the fields of biology, computer science and mathematics. Briefly coined, it is the use of computers to model the living phenomena and simultaneously the study of life to improve the usage of computers. Biologically inspired modeling is a major subset of natural computation. So, let us understand what is ant colony optimization. It is about the optimization, that is the general optimization problem. Given fx r, find x belongs to x such that fx is minimum. Given a graph with two specific vertices a and b, find a shortest path from A to B. So this is a shortest path problem. A polynomial layer given a set of cities and pairwise distances. If the problem is to find a shortest route for the tour, then it is popularly a case of a traveling salesman problem. Given a sequence of amino acids of a protein and you are asked to find the structure of the protein, then protein structure prediction problem can also be done with ACO. Where is my manuscript for the talk? I put it on this pile of papers. So this is a type of problem to solve needle in a haystack. It is also called hopeless problem solving. Now let's come to ACO, how it defines a heuristic optimization method. So the definition is that a heuristic optimization method for shortest path and other optimization problems which borrow ideas from biological specimen, that is the ants. Based on the fact that ants are able to find shortest route between their nest and source of food. Shortest route is found using pheromone trails which ants deposit whenever they travel as a form of indirect communication. So you can see the ants traveling from the nest. They don't know the path which is to be followed. Usually they take longest path towards their food, that is the selected path, and finally the shortest path gets discovered. So what is the ACO algorithm behind it? The process starts by generating m random ants, that is the solution. An ant is represented by k equal to 1 to m, represents a solution string with a selected value for each variable. An ant is evaluated according to an objective function. This objective function we have been done into the simplest linear programming in solver, but in a very basic way if you can just recapitulate it. Now accordingly the pheromone concentration associated with each possible route, that is the variable value, is changed in a way to reinforce good solution as follows. So this is the typical equation for ACO algorithm. Is tau ij in bracket t is equal to rho tau ij t minus 1 plus delta, that is the change in tau ij, where t represents 1, 2 till capital T, where capital T is the number of iterations generation cycles. Tau it, that is tau ij in fact, in bracket T is the revised concentration of pheromone associated with option Lij at iteration t. Tau ij t minus 1 is the concentration of pheromone at the previous iteration t minus 1, and tau ij is equal to the change in pheromone concentration, and rho is the pheromone evaporation rate, that is the 0 till 1. The reason for allowing pheromone evaporation is to avoid too strong influence of the old pheromone, to avoid premature solution stagnation. Now let's come to the traveling salesman problem. Given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city and returns to the original city? It is an NP hard problem, which means that no algorithm exists which can find the optimal solution for this problem in constant time and computation resources. The best we can do to solve this problem is to apply heuristic approaches to find a solution. The ant colony optimization, as you will see, finds the solution to the given problem quite easily. This problem is synonymous with real world scenarios like delivery of postal mail, packages like Amazon does, food delivery that we usually acquainted with online services for the restaurants and their services, etc. Now let's go to the solving TSP problem using ACO in Python, a hands-on implementation. So open Python as usual. Let's come to the Jupyter notebook. Then click new. As usual, we'll click Python 3. I think now you are quite well versed to do that from the CMD, opening the Jupyter one. Next, you click into untitled, name it as ACO, and then rename it for your new coding. Here you put import random. This will import the random library. Then class graph in bracket object. Class will create our state space, that is, it will set up the environment. Next, type def init in bracket self cost matrix list rank init. This constructor will accept cost matrix and rank of the cost matrix, that is the self matrix, equal to cost underscore matrix. Then type self rank equal to rank. Next, self pheromone in bracket 1 divided by rank multiplied by rank for j in range in bracket rank for I in range rank. This is the formula for computation of the pheromones. You have to type it correctly without any spaces or any extra characters. As you have seen, we have corrected the same. Next, type class ACO in bracket object. This is the class which implements ant colony optimization algorithm. Type def init in bracket self ant count int generations int alpha then float beta float then row float then int strategy int. So this is the constructor that accepts number of ants, number of generations, alpha which is relative importance of pheromone, beta which is relative importance of heuristic information, rho which is pheromone residual coefficient, q is the intensity of a pheromone, strategy is the pheromone update strategy. Strategy means ant cycle, 1 means ant quality, 2 means ant density. Now let's update these values. Self q equal to small q, self rho equal to rho, self beta equal to beta, self alpha equal to alpha, self and count equal to and count, self generations equal to generations, self update strategy equal to strategy. Next, type def update pheromone in bracket self graph ants list this function implements the pheromone update function. It accepts our environment which we implemented as graphs and ants. For I row in enumerate graph dot pheromone, for j call in enumerate row graph dot pheromone ij asterisk then self row. Now for ant in ants graph pheromone ij plus equal to and pheromone delta I j. Then we go to the command for solving, def solve self graph in bracket graph. This will implement our solver function. So this is the extension of our solver. Best then cost equal to float, then INF we are setting initial cost to infinity, best solution. For gen in range self generations we will make our ants in bracket and self graph for I in range self and count for ant in ants after this type for ant in ants for I in range in bracket graph rank -1 is ant underscore select underscore next and total cost. Now we will have to write, so type and total cost equal to graph matrix and taboo -1 and taboo 0 if and total cost is less than best cost. So best cost equal to and total cost, best solution equal to, put bracket and add and taboo to update pheromone. Next type and update pheromone delta. Next we will self update pheromone. So type self update pheromone in bracket graph ands print generation best cost path format in bracket gen best cost best solution. So return best solution and best cost. Then press run. So everything has been correctly put into the command because there is no error. If there is an error, then you have to find and correct it where it is and then continue. Class and object will be making ands in this class. Def init self ACO, ACO graph in bracket graph self colony equal to ACO self graph equal to graph self total is the cost, self taboo in bracket taboo list self pheromone delta in bracket, that is the local increase of pheromone, then self allowed equal to I for I in range graph matrix ij for j in range graph rank. So this is actually the nodes which are allowed for the next selection. So let's type next self eta in bracket 0 if I equal to j else 1 graph matrix. Now it's ij for j in range graph rank for I in range graph rank. So this becomes the heuristic information. Next, so after we type the heuristic information, you have to type command start equal to random randinit in bracket 0 graph rank minus 1, that is start from any node. then type self taboo append in bracket start, then type self current equal to start, finally self allowed remove start. Next type def select next self denominator 0 for I in self allowed denominator plus equal to self graph pheromone self current I self colony alpha self eta self current self colony beta no inspection pi unused local probabilities 0 for I in range self graph rank probabilities for moving probabilities for moving to a node in the next step we have to go. So type probabilities I self graph pheromone self current I self colony alpha self so try this one self allowed index I this test if allowed list contains I. Next type probabilities I equal to self graph pheromone in bracket self current I self colony then type alpha then self eta self current I self colony beta then denominator finally you have to type except value error pass means do nothing. Next select node by probability root here selected equal to 0 rand equal to random for I probability this is used to enumerate probabilities So type rand equal to probability if rand type 0 selected equal to I, then break type self allowed, remove selected, self taboo, append selected, self total cost, self graph matrix, self current selected, then self current equal to selected, next def update pheromone delta in bracket self, this is updating pheromones, self pheromone delta equal to 0 for j in range. So once you type self pheromone delta, then you have to type 0 for j in range in bracket, self graph rank for I in range, self graph rank. Next line you type for in range in bracket one length self taboo, so these are the pretty long range of commands you have to put, but if you follow these instructions then it won't be a problem. So type I equal to self taboo, next j equal to self taboo underscore if self colony update strategy equal to 1 and quality system self pheromone delta ij equal to self colony q, then elif self you can copy and then paste and make the necessary changes, because it requires self colony update change for the strategy. So strategy equal to 2, then self pheromone delta ij equal to self colony Q. ELIF self colony update strategy equal to 2 ant density system, no inspection, pi type checker actually it is, then type self pheromone delta ij which equal to self colony Q by self graph matrix ij else and cycle system. Self pheromone delta is self Q divided by self total cost. Next we will be writing helper functions to visualize our output. Run. Since this is a big command, you may find errors and you check in that position as you have seen, and then you can correct it. After that rerun, now it's perfect. In this way you can rectify the errors. Now let's type the helper function. Import operator, import matplotlib pyplot as plt, defplot in bracket points, path list, x equal to in bracket, y equal to in bracket. For point in points, x append point 0. Similarly, y append point 1. No inspection, pi unused local, y equal to list in bracket map operator sub max y for I in range, len points then finally y, then plt plot in bracket x y co for in range in bracket one len path I equal to path in bracket 1 and j equal to path. So these are no inspection pi unresolved references. Next, type plt arrow x I y I x j minus x I y j minus y I color equal to r, length includes head true, that is head equal to true, no inspection pi type checker. Type plt xlim in bracket 0 max x multiplied by 1 multiplied 1.1. This then next is no inspection pi type checker. So type plt ylim in bracket 0 max y, then 1.1, then put plt show. Now let's run. So there is no error. So perfectly the commands are put, and now we are ready to open our data file. Go to the data file. The first value indicates the name of city, example city 0, city 1 or city 2, etc. These two values are x and y coordinate of our city. Our salesman needs to visit each of these cities to complete his journey. Now let's move back to Python Jupyter Notebook. Here type import math def distance city 1 dict city 2 dict. This will return the Euclidean distance or L2 distance. Then return math sqrt function in bracket city1 x minus city2 x, then type 2 plus in bracket city1 y minus city2 y 2 cities in bracket equal to, and then this is a big line of commands. After that there are only two commands, that is cities and then points. With open data CHN31 text as F for line in F read lines, then city equal to line split, then cities append in bracket DICT index equal to INT city 0 close bracket, then x equal to INT city 1, y equal to INT city 2, points append INT city 1, INT city 2. That is, the points append will be INT city 1 and INT city 2. Cost matrix then rank equal to length cities, next type for I in range rank row equal to in bracket for j in range rank row append distance in brackets it is I, so it is j, cost matrix append row ACO equal to ACO 10, 100, 1, 10, 0.5, 10 to graph equal to graph in bracket cost matrix rank path cost equal to ACO solve graph print cost path format cost path plot points path. So finally we have come to the end of our coding. Now we have to check, so let's run. So it was previously we are getting warning message, it was not an error. To get rid of this, you can put here the command no inspection pi unused local. Similarly, insert here no inspection pi unresolved references, and third, then before PLT x lim insert no inspection pi type checker. Finally, before the similarly PLT y lim, before that insert no inspection pi type checker, and then go to run. So we will get, as you can see, the cost of making the journey is 16230.27, and the path taken by the salesman will be 28, 10, 22, 15 entirely till 12. We can also see, check the graph. Each point represents a city here, and the line joining this coordinate is the path taken by the salesman to visit all of them. So this is the most optimized shortest path. Thank you. This is hands-on implementation of mind-spared modeling, and hope this learning session you have enjoyed and understood well. If you have any queries, please contact at this for further clarification.